On June 27, 1942, a Boeing B-17E Flying Fortress, designated My Gal Sal, approached the western edge of the Greenland ice cap. The aircraft was part of a group of bombers, often reported as 13, attempting to ferry across the North Atlantic as part of Operation Bolero. The formation encountered a severe weather front that obscured the horizon and broke their visual contact with the surface. The pilots faced a critical decision between maintaining formation in blind conditions or attempting to locate a gap in the cloud deck. As fuel reserves dropped below the margin required to return to Goose Bay, Labrador, the decision reduced to a single option, which was a forced landing on the glacial surface. The pilot set the aircraft down in a wheels-up configuration. The B-17E is a robust airframe designed to absorb significant punishment, but a belly landing on ice imposes specific structural loads that differ from a water ditching or a runway failure. The ice surface is rigid and often corrugated by wind patterns. When My Gal Sal made contact, the friction generated immense heat and noise, but the airframe did not break apart. The fuselage remained continuous from the nose transparency to the tail gunner station. The 4 Wright Cyclone engines seized or were shut down prior to impact, bending the propellers but leaving the wing roots attached. The entire crew evacuated the aircraft without critical injury. In the immediate aftermath of the landing, the aircraft sat upright on the snow, essentially intact. If this event had occurred in the accumulation zone of the Greenland ice sheet, the aircraft would have been buried by annual snowfall. This is the mechanism that encased the P-38 fighters of the Lost Squadron under hundreds of feet of ice. However, My Gal Sal landed in the ablation zone. This is a specific glaciological region where the net loss of ice mass through melting and evaporation exceeds the net gain from precipitation. In this environment, the glacier surface lowers over time rather than rising. This distinction in location determined the physical fate of the aluminum structure over the next 53 years. The interaction between the aircraft and the ablation zone created a phenomenon known as the pedestal effect. The aluminum fuselage and the broad wingspan of 104 feet acted as a massive sunshade. The metal reflected solar radiation and insulated the ice directly beneath the airframe. While the exposed ice surrounding the wreck melted down by several inches or feet per year, the ice shielded by the bomber did not melt at the same rate. Over the passing decades, the surrounding glacier surface dropped away while the aircraft remained at its original elevation. The result was that the 30-ton bomber eventually sat perched atop a rising column of ice. This instability introduced a new mechanical threat that was far more destructive than the initial landing. The pedestal grew until the center of gravity could no longer be supported by the narrowing column of ice beneath the fuselage. The physics of the environment dictated that the system must eventually fail. When the balance point shifted, driven by high velocity, katabatic winds flowing off the ice cap high ground, the aircraft fell. It did not slide gently, it flipped off its ice pillar. The violence of this secondary impact caused damage that the initial landing had not. The fuselage slammed into the hard ice upside down. The weight of the airframe combined with the rotational torque of the fall crushed the upper turret structure and twisted the main fuselage longerons. The structural continuity of the B-17E relies on the integrity of its semi-monocoque skin and stringers. When the plane flipped, the stress exceeded the yield strength of the aluminum at the rear fuselage production brake. The tail section eventually separated from the main body. By the time recovery teams assessed the site in 1995, the aircraft presented a heavily altered wreck field that differed radically from the clean forced landing of 1942. The fuselage lay inverted and broken. The wings were warped by the uneven surface. The tail section lay separated from the forward structure. This was no longer a simple extraction of a preserved time capsule. The geometry of the wreck had been altered by half a century of thermal dynamics and gravity. The 1995 recovery team, led by Gary Larkins, focused on extracting and preserving the wreck. Discussion of a return to flight existed in some accounts, but the practical objective became transport and conservation. The structural twisting caused by the pedestal collapse rendered a flying restoration technically unfeasible without replacing the majority of the original material. The goal was to retrieve the wreckage for forensic preservation and static museum display. This shifted the engineering problem from aerodynamic fidelity to logistical transport. The team had to dismantle a heavy bomber that was already broken in ways the manufacturer never intended while working on an active ice sheet that continued to shift and melt. The challenge was defined by the separation of the components. The main fuselage section was too heavy to be lifted in one piece by the available light helicopters. The tail was already detached, but the wings remained bolted to the carry through spars. The engines remained mounted to the nacelles. Every bolt and fastener had been subjected to 53 years of deep freeze cycling. The recovery required a reverse assembly process, performed in a hostile environment where temperatures could drop well below freezing even in summer. The stakes of the operation were defined by the rate of structural and environmental deterioration. While the ablation zone kept the plane from being buried, it exposed the aluminum to constant wind erosion and freeze-thaw expansion. Every season, the aircraft spent inverted on the uneven ice increased the fatigue on the remaining structure. The aluminum skin was suffering from cold flow deformation, where the metal slowly changes shape under persistent stress. To save the airframe, the team had to stabilize the structure on site, disassemble it into transportable sections, and fly it out before the glacial movement ground the components into unrecognizable scrap. The recovery was a race against the mechanical erosion of the ice itself. To understand the engineering challenge facing the recovery team in 1995, one must first distinguish between two radically different forms of glacial preservation. A few years prior to the My Gal Sal operation, another team had successfully extracted a P-38 Lightning fighter known as Glacier Girl from the Greenland ice sheet. That aircraft had landed in the accumulation zone where annual snowfall exceeds melt. Consequently, the P-38 was buried under well over 200 feet of solid ice. The recovery required thermal melting probes and a vertical mine shaft. The pressure of the overhead ice had crushed the airframe of the fighter, but the burial had also sealed it in a stable, dark environment with constant temperature and zero wind. My Gal Sal faced the opposite physical reality. Because it landed in the ablation zone, the ice did not envelope the bomber. Instead, the glacier effectively rejected the foreign object, pushing it to the surface. While this made the wreck visible from the air and accessible without deep shaft mining, it exposed the aluminum structure to 53 years of violent atmospheric interaction. The damage profile of the B-17E was not defined by crushing static pressure from above, but by dynamic weathering and thermal cycling from all sides. The most insidious mechanism at work was long-term distortion driven by uneven support, wind loading, ice movement, and repeated thermal cycling. Over long durations, repeated loading and temperature swings can permanently change the geometry of an aluminum airframe, especially when it is supported unevenly. Under persistent stress caused by gravity and the uneven support of the ice, the metal structure began to creep. When the aircraft spent decades perched on its ice pedestal and subsequently flipped upside down, the main wing spars and fuselage longerons were subjected to constant torsional loads. Over 53 years, the aluminum slowly deformed at the molecular level to accommodate this stress. This is not a simple elastic bend that snaps back when the load is removed. It is permanent deformation and structural misalignment that can render major assemblies geometrically incompatible with flight loads. The wings of My Gal Sal were not just broken, they had taken on a set warp that rendered them geometrically incompatible with the requirements of flight. The environment further degraded the evidence through thermal fatigue. In the ablation zone, the airframe was exposed to the full spectrum of Arctic weather. In the summer, the aluminum absorbed direct solar radiation, heating up significantly above the ambient air temperature. In the winter, or during sudden storms, the temperature plunged well below zero. This cycle caused the metal to expand and contract repeatedly thousands of times over the half-century. Each cycle stressed the rivets and bolted joints, loosening the fasteners that held the production sections together. Wind scour acted as a secondary abrasive force. The crash site lay inland from the coast on the approach toward the intended Greenland airfield at Bluey West 8, leaving the bomber short of its destination. This region is subject to katabatic winds, which are high-density gravity-driven air currents that accelerate down the slope of the glacier. These winds carried fine ice crystals that acted like a sandblaster against the exposed skin of the bomber. While the interior of the buried Glacier Girl was preserved like a time capsule, the exterior of My Gal Sal was scoured and buffeted. The wind stripped paint and eroded the thinner aluminum surfaces, while the force of the gusts worked against the large surface area of the vertical stabilizer and the wings, creating a constant leverage that fatigued the attachment points. This exposure created a paradox for the recovery team. Access was physically easier than the deep extraction of the P-38 because the plane was on the surface. However, the structural integrity was significantly lower. A plane encased in ice is supported by that ice. A plane resting on the surface is supported only by its own compromised frame. The recovery engineers had to assume that every load-bearing member was suspect. The main wing spars, which carry the lift load of the aircraft, could no longer be trusted to hold the weight of the fuselage during a lift. The connection points between the inner wing and the outer wing panels were potential failure nodes, where corrosion or fatigue might cause the structure to snap if hoisted incorrectly. The position of the wreck on the ice also complicated the logistics of the workspace. The surface of the ablation zone is not a flat runway. It is a chaotic field of hummocks, ridges, and meltwater channels. The aircraft lay inverted on this uneven terrain, which meant there was no flat level datum from which to measure or stabilize the hull. The team could not simply jack the aircraft up because the ice beneath the jacks would shift or melt under the pressure. Every movement of the heavy components had to account for the lack of a stable foundation. Ultimately, the physics of the ablation zone dictated the scope of the project. If the aircraft had been buried, it might have been a candidate for restoration to flying condition despite the crushing damage because the metal would have been chemically preserved. Because it was exposed, the cold flow and thermal stress had warped the primary structure beyond the limits of safe flight. The Glacier had spared the aircraft from being lost forever, but it had exacted a heavy price in structural fidelity. The recovery team had to accept that they were not rescuing a potential warbird, but rather salvaging a massive, compromised artifact that required immediate stabilization to prevent total disintegration. The decision to recover the B-17E in 1995 relied on a specific procedural choice regarding the integrity of the airframe. The team led by Gary Larkins faced two options for reducing the 104-foot wingspan and 74-foot fuselage into transportable loads. The first option was to cut the structure into arbitrary segments using saws or torches. This method is fast and requires little technical finesse, but it permanently destroys the historical fabric of the artifact. The second option was to reverse the original manufacturing process. This approach required the team to locate the factory unions known as production breaks and mechanically unfasten the aircraft bolt by bolt. Larkins chose the second path. This decision transformed the operation from a simple salvage job into a complex field engineering project conducted in a remote camp on the ice. The team lived on the glacier for weeks, establishing a work rhythm dictated by the daylight and the temperature. Unlike the modern heavy lift infrastructure available at established airbases, the recovery site was limited to portable generators, hand tools, and manual rigging equipment. This was not the first time a team had trekked to the site to remove hardware. In July 1942, just 1 month after the crash, a small expedition returned to My Gal Sal using dog sleds. Their objective was not the airframe, but the highly classified Norden bomb site located in the nose. At that time, the technology was considered too sensitive to leave exposed on the ice even in such a remote location. The 1942 team extracted the site and departed, leaving the bomber to the elements. 53 years later, the 1995 team returned to finish the job of disassembly that the dog sled team had effectively started by leaving the bulk of the machine behind. The technical key to this disassembly was the production break. A B-17 is not built as a single continuous monolith. It is an assembly of discrete sections manufactured separately and joined at the final assembly line. The fuselage is divided into fore and aft sections bolted together at a heavy transport joint. The wings are attached to the fuselage at the wing roots by massive terminal fittings. These joints are designed to hold the aircraft together under the extreme loads of combat and turbulence, but they are also designed to be reversible. Locating these brakes on a pristine aircraft is straightforward. Locating them on a wreck that has been inverted, crushed, and weathered for 5 decades presents a different challenge. The skin of the aircraft often overlaps the internal structural joints, hiding the bolts from view. The recovery team had to peel back damaged aluminum plating to access the heavy steel bolts that connected the main spar cords. The challenge of the production brake is the condition of the fasteners. The B-17 uses steel bolts driven into aluminum structure. Over 53 years, moisture enters the threads and creates a galvanic reaction between the dissimilar metals. The steel corrodes and expands, seizing the bolt within the hole. The team had to apply penetrating fluids and carefully modulated torque to break the bond of the corrosion without shearing the bolt heads or cracking the surrounding aluminum alloy. If a bolt sheared inside the fitting, it would require drilling out a precision hole in the field, a risk that threatened the timeline of the operation. The disassembly sequence followed the distribution of weight. The engines were removed first. Each right cyclone represented a dense mass at the leading edge of the wing. Removing them shifted the center of gravity of the remaining wreck. Then the outer wing panels were unbolted from the inner wing sections. This reduced the leverage acting on the fuselage. Finally, the fuselage itself was separated at the transport joint. This process required a keen understanding of structural tension. As the aircraft lay upside down on the uneven ice, certain sections were under compression while others were under tension. Removing a structural bolt in a tensioned area can cause the assembly to spring apart violently, much like cutting a taut cable. The team had to support each section with blocks and straps before the final fasteners were withdrawn, ensuring that the separation was controlled rather than kinetic. The working conditions imposed a hard limit on efficiency. The team was working with bare hands or thin gloves for dexterity when manipulating small tools, exposing them to the biting cold. The metal of the aircraft was a heat sink, draining thermal energy from anyone who touched it. Yet the discipline held. By locating and utilizing the production brakes, the team successfully reduced the 30-ton bomber into a series of modular components. They had not cut the plane apart, they had simply undone the work of the Boeing factory floor from 1942, preparing the machine for its final flight not under its own power but suspended beneath a helicopter rotor. The operational limit of the 1995 recovery was defined by a single non-negotiable number, which was the external lift capacity of the AS-350 A-Star helicopter. This light utility aircraft was the primary lifting asset available to the team. Unlike military heavy lift operations that might utilize a twin-rotor Chinook capable of lifting 20,000 pounds, the A-Star is limited to a fraction of that weight. This created a hard mathematical constraint. The empty weight of a B-17E is over 30,000 pounds. Even when disassembled into major components, the individual sections of the fuselage and wings threatened to exceed the safety margin of the helicopter, especially when operating at the density altitude of the Greenland ice cap. This weight mismatch dictated a strict protocol of aggressive stripping. Before any major section could be rigged for lift, the team had to remove every pound of non-structural mass. The 4 Wright Cyclone R-1820 engines had already been detached during the disassembly phase. These power plants are dense, concentrated masses of steel and aluminum alloy. Leaving them attached to the wing sections would have made the lift impossible. They were rigged and flown out individually, treating the engines as discrete cargo loads rather than airframe components. The challenge extended beyond simple mass. The recovery team had to master the physics of transport geometry. Lifting a fuselage section on a long line is not like lifting a block of concrete. The fuselage is an aerodynamic shape designed to interact with airflow. When suspended beneath a helicopter moving at 60 knots, the cylindrical section of the bomber acts as a chaotic airfoil. If the sling rigging is not perfectly centered relative to the center of gravity of the load, the section will begin to rotate or swing. A destabilized load can build up enough oscillation to threaten the stability of the helicopter itself, forcing the pilot to jettison the cargo to save the aircraft. To control this risk, the team had to design specific rigging harnesses for each component. The forward fuselage containing the cockpit and the nose station had to be hung so that it flew nose forward into the airstream, streamlining its profile. The wing panels had to be suspended in a way that prevented them from generating lift, which would cause them to kite upward and slacken the line before snapping it tight again. This required a precise calculation of the sling geometry, adjusting the length of the straps to force the awkward aluminum structures into a stable flight attitude. The destination for these loads was a staging area near the coast, not the original intended destination of Bluey West 8. In 1942, the crew of My Gal Sal had been aiming for that airfield when they ran out of fuel 26 miles short. In 1995, the recovery team used the coast as a transfer point. From the ice, the parts were flown to the staging ground. From there, they were loaded onto a barge for the long sea transit to the United States. This multimodal logistics chain meant that the airframe had to be handled multiple times, increasing the risk of handling damage with every transfer. The window for this aerial convoy was governed by the unpredictable weather of the ablation zone. The A-Star could not operate in high winds or whiteout conditions. The team had to stage the loads and wait for clean air. When the window opened, the operation became a continuous cycle of flights shuttling the dismantled bomber piece by piece off the ice. The pilots had to manage the fuel load of the helicopter, carefully trading fuel weight for cargo capacity to maximize the margin of safety on each lift. As the components left the ice, the physical footprint of the crash site began to vanish. The four engines, the outer wing panels, the stabilizers, and finally the two halves of the split fuselage were lifted into the sky. What remained on the ice were the small scraps and debris that did not merit preservation. The heavy lifting phase proved that the disassembly strategy had been correct. By breaking the aircraft down at the production breaks and stripping the heavy internals, the team had successfully adapted the massive strategic bomber to the limitations of a light civilian helicopter. The geometry of the lift held, and the airframe was successfully extracted from the environment that had claimed it 5 decades earlier. When the components of My Gal Sal arrived in the United States, the operation shifted from a recovery challenge to an engineering assessment. The aircraft was no longer fighting the ice of the ablation zone, but it now faced a critical decision point that defines the world of aviation archaeology. The recovery team and the subsequent restoration group led by the Ultimate Sacrifice Memorial at the Blue Ash Airport in Ohio had to determine the final configuration of the airframe. The popular assumption regarding recovered World War II aircraft is that the ultimate goal is always a return to airworthy status. The sight of a B-17E taking flight is a powerful emotional outcome, but engineering decisions are not driven by emotion. They are driven by the material reality of the aluminum. The assessment revealed the full extent of the damage caused by the pedestal flip. While the aircraft had looked largely intact from the air in 1964, the physics of the flip had compromised the primary load-bearing structure. The main wing spars, which act as the spine of the aircraft, had been subjected to 53 years of cold flow deformation and a violent torque event. In metallurgy, aluminum does not possess a fatigue limit like steel. Once it has been plastically deformed, it cannot simply be bent back into shape without inducing work hardening and micro-cracking. To return My Gal Sal to flight status would require the complete fabrication of new wing spars. This led to the fundamental trade-off between restoration and conservation. A restoration focused on airworthiness prioritizes the function of the machine. To make the B-17 safe for flight, the team would have to drill out tens of thousands of rivets, remove the twisted longerons and warped skins, and replace them with newly manufactured aluminum. By the time the process was complete, the aircraft would be a B-17E in shape and capability, but it would consist largely of modern metal. It would essentially be a data plate restoration where the identity of the aircraft is transferred to a new structure built around the original serial number plate. The alternative was conservation. This approach prioritizes the preservation of the original material even if that material is no longer structurally sound enough for flight. The goal is to arrest the decay and stabilize the artifact as it exists. For My Gal Sal, the history was not just in its design, but in its specific scars. The bent aluminum told the story of the ice pedestal. The corrosion told the story of the exposure. Replacing that metal to achieve flight would mean erasing the physical evidence of the events of 1942 and the subsequent half-century. The team selected the path of static preservation. This decision was not a concession of failure, but a deliberate choice to maintain the historical integrity of the airframe. The objective became to reassemble the aircraft so that it appeared visually complete while accepting that it would never again endure the loads of takeoff. This allowed the team to retain the majority of the original skins and internal structure, including components that would have been rejected by the Federal Aviation Administration for a flying aircraft. The execution of this static plan was neither short nor simple. It required 12 years of labor to reverse the entropy of the glacier. The workforce consisted primarily of volunteers who dedicated over 90,000 hours to the project. Their task was to disassemble the subcomponents, clean the corrosion that had formed in the galvanic traps between the steel fasteners and the aluminum sheets, and reassemble the airframe using corrosion-inhibiting compounds. They had to untwist the fuselage enough to align the bolt holes at the production brakes, but they did not have to stress the airframe to flight tolerances. The restoration process also had to address the missing pieces. The tail section, which had snapped off during the flip, required extensive reintegration. The top turret area, which had been crushed when the plane landed upside down, required complex sheet metal work to regain its profile. However, because the goal was static display, the team could use original damaged parts that had been straightened for cosmetic fidelity rather than structural strength. This kept the percentage of original 1942 material exceptionally high compared to airworthy warbird restorations. The project reached its conclusion not on a runway but in a preparation for suspension. The restoration team prepared the aircraft to be hung from the ceiling of a museum. This required the design of a custom internal cradle system that could distribute the weight of the 30-ton aircraft through specific hardpoints on the airframe. The spars that could no longer support flight loads were sufficient to support the static weight of the aircraft when supported from above. By choosing the static path, the team succeeded in saving My Gal Sal as a document of history rather than converting it into a generic flying replica. The trade-off was absolute. The aircraft would never fly again, but it would remain the actual machine that landed on the ice on June 27, 1942. This marked the successful completion of the recovery objective. The aircraft was off the ice, it was chemically stabilized, and it was structurally reintegrated. The timeline of decay that began in the ablation zone was effectively halted. Today, the physical evidence of the My Gal Sal recovery operation hangs suspended 80 feet above the floor of the United States Freedom Pavilion in New Orleans. The aircraft is the centerpiece of the National World War II Museum Aviation Collection. Its position in the Boeing Center allows observers to view the airframe from multiple angles, including from walkways that align with the fuselage level. This specific display configuration is the direct result of the technical decisions made during the recovery and restoration phases. Because the team chose the path of static conservation rather than structural replacement, the aircraft exists as a verified primary source document of the early warfare routes. One of the most critical pieces of evidence attached to the airframe is not the serial number plate on the instrument panel, but the preserved saw-cut propeller. This single component validates the entire survival narrative of the crew. When the aircraft is viewed from the gallery, a keen observer can note a distinct anomaly on the propeller blades of the outboard starboard engine. The tips of the blades are not factory smooth. They are rough and irregular. This is not damage caused by the impact with the ice, nor is it corrosion from the ablation zone. It is the result of a deliberate field engineering modification performed by the crew in 1942. After the crash, the crew faced a critical survival constraint. They had a radio transmitter, but the batteries were drained. To send an SOS, they needed to generate electrical power. The only generator capable of functioning was attached to the number 4 engine, but the propeller on that engine had been bent during the belly landing. If the engine were turned over, the eccentric mass of the bent blades would create a vibration violent enough to tear the engine from its mount. The crew did not have heavy tools or replacement parts. They had a hacksaw from their survival equipment. The crew manually cut the tips off the aluminum alloy propeller blades. They did not measure with precision instruments. They cut by eye, removing the bent sections to balance the rotating mass. This crude reduction in diameter severely reduced propulsive efficiency, but it improved balance enough to allow the engine to run at low revolutions per minute without tearing itself apart. This generated the voltage required to power the radio and transmit the signal that eventually led to their rescue. The restoration team preserved these saw marks. They did not file them down or replace the propeller with a pristine surplus unit. This adherence to the evidence discipline ensures that the aircraft tells the story of the crew's competence rather than just the manufacturer's design. The airframe itself represents a rare technological snapshot. My Gal Sal is a B-17E model. The vast majority of surviving flying fortresses are the later G models produced in massive numbers near the end of the war. The E model features a different tail geometry and fuselage configuration reflecting the design philosophy of 1941 and early 1942. By recovering this specific serial number, the team saved a variant that had largely disappeared from the inventory. It documents the transition period of heavy bomber design before the introduction of the chin turret and the massive production surges of the mid-war years. The logistical finality of the project occurred when the restored sections were transported from Ohio to Louisiana. The aircraft had to be moved into the museum pavilion before the building was fully enclosed. Once again, the size of the airframe dictated the sequence of construction. The wings and fuselage were positioned and the building was effectively completed around them. This creates a permanent enclosure. The aircraft is no longer subject to the wind scour of the Greenland ice cap or the thermal cycling of the ablation zone. It is held in a climate-controlled environment where the relative humidity is regulated to prevent the reactivation of galvanic corrosion between the steel and aluminum components. The suspension system that holds the 30-ton bomber aloft utilizes the hardpoints identified during the restoration engineering assessment. Steel cables connect to the wing spars, transferring the load to the roof trusses of the pavilion. This static load path is fundamentally different from the aerodynamic lift loads the spars were originally designed to carry. In flight, the wings bend upward as they support the fuselage. In the museum, the wings hang from the cables, and the fuselage hangs from the wings, creating a tension reversal in certain members. The restoration team verified that the structure, even with the history of cold flow deformation and twisting, could sustain this static load indefinitely. The recovery of My Gal Sal is classified as a complete success within the parameters of the defined objective. The mission was not to return a ghost to the skies, but to extract a threatened artifact from a hostile environment. The outcome path selected was one of preservation over operation. By accepting the limits of the damaged aluminum, the team ensured that the original material survived. The entropy of the glacier was halted. The aircraft no longer rests on a shifting ice pedestal. It rests on a calculated web of steel cables serving as a fixed reference point for the history of Operation Bolero. The cycle of decay has been broken and the evidence is secured.